Good morning, everyone. Welcome back. Day after the midterm. Midterm went very well last night. You guys are, I think, starting to understand what is expected of you. And we made a huge effort, the whole team, to make the exam readable and fair. So the average was 70 with a median of nearly 75. And if you know your math, median is the you just count half the grades are above the median, and half the entries are above it, and half the entries are below it. So over half the people got the above the average, and half the people got above 75. So everybody did quite well, and you should be pleased with that. So we're back on track, and like you said, we're going to adjust that first midterm. And I have to apologize again. I did not realize that the actual scores for these midterms aren't showing up on your B courses. Apologize for that. We're going to fix that today. I wasn't aware of it, and it's hard for us. It's hard for me. I don't know if any of these guys can do it, but it's hard for me. There's a student view, but it's still hard to see what a real student sees in the grade book. So, but we'll get the scores up today, and you can see how you did. The answers are released Friday morning, like last time. So you'll be able to look at the answers and grade your own, I think, either way. So let's go back to it then. We have been talking about trends on the periodic table, and we saw these interesting trends last time. And I was rushing last time so much that I don't think I gave a very clear explanation of these interesting full and half full shells, quantum shells, L values. So the filling of an N value, the filling of an L value is a state of low energy. It's interesting. I'm trying to think back. It just occurred to me just this second. I'm trying to think what it is actually. This is empirical again. So these are measurements that we're showing you here that indicate that these are these full and half full shells are lower energy than the shells around them. But I forget, and it's going to bug me now. I'll have to look afterwards what it really is about the quantum calculation that gets you there, or if the quantum calculation even actually predicts it. It predicts radii very well. But as I told you, the quantum mechanical, the mathematical description of multi-electron atoms or molecules is very much approximations. It's approximations and approximations. You take the hydrogen atom, the perfect mathematical explanation, but once you add one more particle, go from 2 to 3, then you have to start making approximations. And what we do is we add different mathematical pieces on top of it and churn through numbers. And what we try to do is match what we see experimentally, like you always do in science. I forget what the actual tweak is that makes these match exactly. And it doesn't matter for you. I just occurred to me that I don't remember. What all we care is that empirically, the numbers we understand, whether or not we understand where the quantum mechanics predicts them. So we saw, especially these numbers here, the numbers in green are endothermic. So these are absorbing energy, and these are ionizations. So all the ionizations, of course, if you're going to pull two unlike charges apart, that always requires energy. The electron affinities interestingly, so this second column, some red, some green. And when they're green, when they're endothermic, they're not very big numbers, but it's quite dramatic that most times for virtually all the elements, there is a positive charge at the nucleus, and a free electron, they do these things in the gas phase, so you'll have gas phase atoms and an electron. It's lower energy for those to be associated with each other. And I think that should be kind of intuitive. There is plus charge showing through. Z effectives aren't perfect, so you see a random negative charge will see a little nuclear charge and be attracted to it. So in general, this is the case. And I drew pictures and I did a really horrible job. You understand, now you know me quite well. One of the reasons we have this PowerPoints is my penmanship and board skills are atrocious. So part of it is I don't practice, and I'm trying to go quickly. I'm just super careless in general. So I'm going to try to be more careful because this is an interesting point. And we wrote down the expressions here. So I'm going to write them down again. We said if you had this beryllium, and if you're going to ionize it, you're going to take beryllium and you're going to go to beryllium plus and a free electron. And we said the energy of this system, these things are exothermic. I'm doing it again. These things are endothermic. You have to put energy in to do this. This state, beryllium plus a free electron, is higher in energy. Actually, kind of matters that that's a free electron. It's hard to get the energy of just the Be plus without this system. You wouldn't want to compare them anyway. You wouldn't want to compare systems with different numbers of electrons. But we also saw here for the beryllium and all these, so this could be any of the elements that I've left here. We saw that if you take beryllium, the neutral element, and you add an electron, and you go to Be minus, that's also slightly endothermic. So these things, that means these are the higher energy states. So here, beryllium, the atom, is lower in energy than both the plus ion and the minus ion. And that is the point. So you have 1s2, 2s2. So you've closed that s orbital, and the filling and closing says, well, adding another electron would go to a 2p electron. So that's the electron configuration of Be minus. And that is a slightly higher energy state. And 1s to 2s1, removing one electron, is a very much higher energy state. So you have the landscape where the beryllium minus and the beryllium plus, and I'll put the electron there for both of them. The beryllium atom is down here. So the 1s2, 2s2 is the lower energy state compared to adding or subtracting an electron. So, and you may have heard people tell you in the past that these full and half full shells are stable. And that is what they mean. And that's why we're here in Chem 1 at Berkeley. We don't want to call things stable necessarily anymore without, we can use that word, but without an understanding of this is what we're talking about. It's local minimum in energy. So if you're going across the energy landscape and you have all these states accessible to you, this is the lowest energy state. I'm pretty sure that this has something very specifically to do with M sub L. I'm sorry, M sub S is giving us a big part of this. Oh, I don't have to erase. All I have to do is go back to the PowerPoint. Okay, so let's move on then. We talked about the periodic trends, and you did this on the demonstration. You did this on the exam last night, so now you guys have seen this several times, and you've even studied it and thought about it for quite some time. So you had something like 5 or 6 minutes to look at this in detail along the several questions. So we see the trend. Ionization energies increase as you go across the periodic table. There are these areas that we understand now that here the 2p3 state, this is the ionization energy. So remember, this is how much energy you put in. So if you're putting the stability, if you're putting the energy of those states, that's the reverse of that. Going from P3, P4, P2. So you can go to this, just fade to the board so they can see that a little better, what I'm drawing there. And the reason I say the energy, you're putting in energy here. This one is, you have to put energy to get to there. So that indicates that these states around it are the lower energy states. Okay. So we talked about these already. This kind of stuff was on the exam quite a bit last night. So you've thought about this. This, very importantly on the exam, we had these isoelectronic species, but it was crucial for us to know that, and I make a bigger deal out of this than most people, I think, but if we don't look at those, these are all isoelectronic, and we cannot tell from the electronic structure what the element is. And I make a big deal of that for several reasons. I want you to know, and I've said it many times, if you take nothing else home from Chem 1, it's the number of protons in the nucleus that determines the element. Because the electrons don't care. The electrons just see plus, and they get trapped in this well of pluses. They see, oh, there's a big potential well, get trapped in there. They do their standing waves about that plus. The nature of the formation of the plus and minus pairs is a natural one, no matter what the element is. Okay, and it's the same for all the elements. So I have to give you, someone has to tell you the exact charge on the nucleus, and then you know the element. So here's where we stopped last time before we went into our review. Electronegativity now is a periodic trend. And this one is semi-empirical in that there's not one experiment that measures electronegativity. Electronegativity is a catalog. You go through and you look at a bunch of data and you say, in a bond, where are the electrons spending more time? Where are the high amplitude wave functions when you form a bond? And we're going to do that here very shortly, is we're going to take our quantum mechanics of atoms and go to quantum mechanics of molecules. And we have different characterizations of bonds depending on how polar they are. Electrons are rarely shared equally between the elements that are bonded together. And that difference, where the electrons spend more time, where the higher amplitude wave functions are, is called electronegativity. The higher your electronegativity, the more the electron wave functions are center on your nucleus. So the electronegative elements are electron withdrawing from the bond. They draw them to themselves. And that trend, these are the electropositive, these are the electronegative. So electronegativity increases kind of diagonal as you go across here. We saw the effective nuclear charge increase as you go across, and you say, well, the effective nuclear charge, if that's getting bigger, that should make me electronegative. That should attract electrons. If I have a bigger effective charge, I'm better at attracting it. And the radius makes a difference too. That bigger radius makes you less able to attract electrons to yourselves. And we'll talk about these definitions more, but I will just tell you, we won't even go through these numbers really. All I'm going to tell you is covalent bonds and ionic bonds are two extremes of that sharing. So ionic bond, it's a complete one electron goes to the other element. So that's as electronegative as you could be. So one element gets all the negative, gets the full electron, the other becomes a plus ion. And those then, the electron is not so much forming the bond, it is the plus charge left over here and the minus charge acquired here holds it together. So it's a Coulombic interaction. And you can have any mixture of covalent where there's perfect sharing of the electron. And we don't understand what sharing can mean in terms of electrons. This we understand, transfer one to the other. Sharing, we're going to explain quantum mechanically. Okay, so for which X, so X can be this molecule here, X can be either iodine, bromine, or chlorine. And I'm going to do this reaction, hydrogenate the chlorine to make HXs. So break those two bonds, form those two bonds. What is the release in energy? Which X releases the greatest amount of energy? And we'll talk through this one first this morning. The strongest of the bonds is the most polar of the bonds. So as you get bigger charge separation, you go more polar. Ionic bonds, incredibly strong. That's the extreme. As you go towards covalent, the more you share the electron, the bond becomes weaker. So of those, you say, well, which is the most polar? And you determine which is the most polar by the biggest difference in electronegativity between the two. So H and Cl, H is over here for all of those. The question is chlorine, bromine, iodine, kind of in a funny place. Not sure where they ended up there on the periodic table. As you know, they're quite a bit farther over here. Chlorine, bromine, and iodine are in that upper high electronegative area, and hydrogen is the same for all of them. So the chlorine is the most electronegative. That makes HCl bond the most polar. So chlorine is the most electronegative. It pulls electrons away the most. Iodine pulls them away the least. This is the most polar interaction. That's the strongest bond. And if you're forming those strong bonds, that's releasing energy. Sometimes that's counterintuitive for people to think of. I make a bond, I release energy. Always think about it the other way. If you have to break the bond, you got to put energy in. You understand that? I have to pull it apart. So going this way has to release it. If going this way, you have to put energy in. Okay. Oh, cool. So next topic. So now we are going to talk about bonds. And we're going to talk about bonds first in terms of very simplistic formalism. This is electron dot structures. If you had any chemistry at all, you've drawn electron dot structures where we use dots for the electrons, and we say, how are they arranged about the atoms? Absolutely no connection to reality. So, but even though it has no connection to reality, we talk about it for two reasons. One, no connection to reality, but handy. It has very good predictive power because it reflects the quantum mechanics to a certain extent. And of course, Gilbert Lewis, here at Cal. So another of our patriarchs, Lewis Hall is right across the street from us. So it's predictive power. It's used throughout chemistry. And especially when you go on and take organic chemistry, we call the organic chemists, we call them cooks because we disparage them in all kinds of ways. But they're also electron pushers. They just push little electrons around their dot structures. Some of you may become electron pushers and cooks. I hope you do, some of you. So what we have here are, I've just taken bits of the periodic table, the S block and the P block. And I've written the outermost electrons. So the n equal 2 electrons here and the n equal 3 electrons here, and just counted them off from 1 through 8. 2 S's, 6 P's, 8 electrons by the time you get there. And I've arranged them in dots about the elements. We call those electrons valence electrons. The outermost shell of electrons are called valence electrons. And even if you haven't done a Lewis dot structure before, you can probably guess what we're going to do next. We're going to bring the elements together and make the bonds share or donate electrons, push these electrons around in dots and pairs to see what the bonding structure might look like. And it's remarkably powerful for such a hand-wavy thing that should not work, really. It's based upon a relatively straightforward fact that quantum mechanics does predict, and that is having 8 electrons in the valence shell is a low energy state. We saw that. So sp6 is one of those where the ionization energy and the electron affinity are endothermic, so it's a low energy state. So if you can get the elements, even in molecules, to have 8 electrons, that replicates the closed 2s or sp quantum shell, and that's what lends the stability, the low energy to the bond. So we call the full shell, it's an octet because of 8 electrons. It's a state, helium. We'll move helium over here. That's why helium is kind of on this side of the periodic table, is its shell is closed. There are no more electrons left to put in. So 2s2 is also one of those dips in those low energy electron configurations. So that's why you see that over there on the periodic table, when by all rights, helium really should be over here. So here it is. We'll just go through this. This isn't a surprise to anyone. Ionic bonding. I'm going to take an electron from one element, put it on another element. And when I do that, I get a positive charge on this element and a negative charge on this element. And we understand what I've shown here. This larger radius, when it went to a positively charged species, that radius decreased. Now there's more positive charge at the nucleus than there is negative around it, and that radius contracts. All the energy levels are closer together. The opposite occurs, of course, you add an electron. So the ionization energy and the electron affinity are both in there to a great extent. So the Coulomb attraction, and when I say Coulomb attraction, I know the words, there's a lot of vocabulary, and this one isn't even particularly, the physicists claim that word. All it means is plus minus attraction. So the plus minus attraction, the Coulomb attraction, is what holds those guys together rather than sharing electrons. So it's not a sharing situation. And here it is. So lithium fluoride, lithium plus and a fluorine minus, and that forms a bond. Or sodium chloride, Na plus and Cl minus after the electron transfer. And then these are salts, we call them. They are ions held together in both the crystal, sodium chloride crystal, you've seen salt, it's a solid, and in solution, if you dissolve them, sodium stays positive and Cl stays negative. So that electron really did transfer from one to the other. If you pull them apart in solution, sodium stays positive. It releases its electron, chlorine minus. And we kind of understand that because that has 8 and that's happy. And sodium now lost its S electron and you're down to the shell below that is full, which is stable. Okay, and you could do it with more than one. You could take magnesium and give, it has S2, give electrons to each of 2 chlorines and form an ionic salt magnesium dichloride. So this comes, as we know, from the electron affinity and ionization energy. They're both in there. You have to ionize one, and then the electron affinity of the other one comes into play. And we've seen that, how that would help. Because chlorine, when you go to Cl minus, here the electron affinity helps you form the bond that releases some energy. But you still have to ionize the other thing. So there's some kind of balance between ionizing those guys and ionizing these guys in the opposite way, adding an electron here, taking it off here, you have to put that energy in, but adding it to the other guy, you get some of the energy back. And notice only some of it. So it's not overall just that interaction, just the balance of those 2 energies is not enough. The rest of it comes, the rest of the exothermic formation of those ionic bonds comes from that Coulomb attraction. So you do the transfer, ionization energy and electron affinity, but then you get plus minus attracting each other and you form tightly packed pluses and minuses together. And this lattice, they're called lattice when you look at organized things in 2 and 3 dimension. The organization of pluses and minuses tightly packed together is very high, very highly exothermic to form that. Very low in energy. And this you don't have to know for any real exam question. It's just neat that these form cubes is the most stable. And here's a electron micrograph of the cubic structure of salt, many salts. And here it is for sodium iodide. And it's interesting that if you look at the salt forming and you do kind of a mass spec experiment on it, the salt prefers certain size crystals. So you get lots at 62 units, 71. And that's kind of a neat quantization of objects. Some cubes are more stable than other cubes, so they form better. So the lattice energy, the plus minuses is more favorable for some cubes than others. Okay, so let's do a Chem Quiz. Which element forms a bromide? So is it calcium bromide, potassium bromide, or neon bromide that's 80% bromine by mass? And here are the relative masses. So you can do the quick calculation. It's relatively easy to get to 80% using those masses. And we've written calcium and potassium about the same just to make it easy. So let's think about that for a minute. So we'll take a vote. I'll start a poll, hopefully, with the new, we just got a new version of, oh goodness. I can select apparently which thumbnail you see now. Show thumbnail of yes. Go. I don't want to do those 2 steps. I hope I don't have to do those 2 steps all the time. Now I can see what your screen capture is on your iClicker software. Okay, let's talk about that for a minute and we'll take a vote. Okay, well, think about coming back together here. Apparently, I have 4 responses, and I'm hearing from the breakout rooms that you can't respond and that iClicker is not working. I'm going to stop and restart iClicker here to see if that helps. I did upgrade it this morning. Never do that. But that upgrade, and today we'll try to send out an announcement. Guys, remind me, send out an announcement. Everyone should upgrade on your end too, just in case there's an upgrade there. So we're all using the same version. Oh my goodness. Ember Mug. Yeah, I'm going to recommend Ember Mug. Are they a sponsor? No. So this is an electronic app-controlled mug that keeps your tea or your coffee or whatever hot beverage you want exactly at the temperature you want it for a couple hours. It's wonderful. So, you have tea and it's sitting there for a while, you go back and it's all cold. Every time I sip this, 134 degrees Fahrenheit. Ember. We have to get sponsors. Okay. So I'll stop this and I will try to restart the software during the next Chem Quiz and see if that helps us. We'll just talk through it for now since we can't really see your answers. So you are going to start doing this all the time now. You draw the electron configurations out. You start to draw the Lewis structure and you say, what's just possible to even form that bond? And bromine, neon is not going to give up an electron to bromine. Neon already has that closed shell that's low in energy. No incentive to give it to bromine. Potassium, yes. That's electronegative. This is electropositive. It has an s electron. So that is absolutely a Br minus K plus situation. However, that one's not going to be 80% by mass. Calcium, 2 s electrons, give 1 to each bromine, form Ca plus 2 that attracts that minus bromine and that minus bromine. So overall, it's neutral. You didn't make or you didn't create or lose any total charges. So that's all neutral. And then this one is a calcium and 2 bromines is 80% by mass bromine. Okay. So that brings back all of our early chemistry with our very latest chemistry. So at which radius does the electron jump from one to the other? So now you have the two elements coming together. The electron has to transfer from one to the other. The question is, does that matter how close they are? I think you'll say it does, because how close they are, certainly once they become plus and minus, that distance matters, because that's the potential energy. That sets the potential energy of the bond. But if you're talking about chlorides, and sodium chloride, lithium chloride, or potassium chloride, where is it easiest, essentially, for the electron to jump over? Where is the, as they come together, which does the bond start to form first? Where does the electron jump from here to here? Talk about that in your breakout rooms. I'm going to restart the software, see if that helps. And why don't you guys restart all your software? Wait for me and then restart. You can even update your software. It probably won't take very much time. I'm going to actually end the entire show, because that probably too many things going on at once will kill us. I will try to now end this, end the session, end the class, and end the class and quit the software. And then I will restart the software if I can. You don't have to listen to me. Okay, so I've restarted the software. You guys can restart. I'm just going to go through this Chem Quiz. I'll just talk through it. And we will get back to this. I'm going to drag this over here. That's where I like it. I have this thing called roster. Okay, so I can see 45 attendees. So maybe those are the people that quit and restarted. And look at that. The absent and the attendees is changing. So you guys are joining. I can see it happening in real time. That's a new feature of the software. Like, we really need that. Although I do often ask how many people are there. So I guess we do need it. We'll start it on the next one. So this, remember, so now we're going to jump back in time to almost the second day of class. And we said, yeah, these two things come together. As they come together, as R gets smaller, the energy decreases. And you say energy increases with R, it gets bigger as you pull them apart. Bigger meaning closer to zero. We put the zero energy here. So higher energy as you pull them apart. That's what we want. That's high energy. Low energy situation where you have that strong potential interaction is down here. So this is telling you that idea of pluses and minuses coming together and getting that strong interaction. And when does that happen? Well, when that is such that you say the jump is going to be favorable, then you do the jump of the electron from one to the other. So we talked about that. That was just a jump back in time. So this is going to happen then here. Potassium has the lowest ionization energy. So everything else is about the same. So when they come together, when the electron jumps, then it's just a plus and a minus attracting each other. It doesn't matter whether it's sodium, potassium, or chlorine. It's just a plus minus attracting each other. So that doesn't matter. What does matter is how easy then it is to remove the electron. So potassium having the lowest ionization energy, the easiest to ionize, that will jump first. And then you have to get closer with the other guys because you can think of it as I got to pull that electron off. I have to be closer to do it because that electron is more tightly held. Or more formally, you say, well, I have to get to this radius because that's how low I have to be in potential energy to balance that moving the electron from one side to the other, because that takes energy. So you want to get it back immediately with your potential energy of your interaction. Okay. So there it is. Lowest ionization energy. Lithium is the highest ionization energy. So I have to get quite close together. And the best lowest ionization energy, which I think is what the question was, is potassium. So potassium chloride forms. Let's talk about the other kind of bonding. That's straightforward. Now I'm going to share the electrons equally. My goal is the same, is to get this configuration around both atoms to have 8, or in the case of hydrogen, 2. So there's a duet that's low energy, and there's a octet that's low energy. So I try to get there. I can do it by sharing the electrons rather than donating electron. So that's the difference between covalent and ionic bonding. There is no full charge separating on either ion. It's a shared interaction. So this electron and this electron bring that together to fill the either fill the octet or the duet. We start calling these bonds now. So pairs of electrons become bonds. So here, that's a single bond, and that is a single bond. So it's a single covalent bond. That sharing one pair of electrons gives you one bond. These electrons are called lone pairs. So chlorine has them, and it's using them to get that stable configuration, that low energy configuration, and it uses a combination of one bonding pair and 3 lone pairs to get to 8, and hydrogen uses a single pair to get to the duet that's stable. Oops. And of course, these are homonuclear. It could be heteronuclear, and most of the interesting ones are heteronuclear. These are perfectly covalent because they're equal electronegativity by definition. Heteronuclear are not perfectly covalent. They're the ones that are polar covalent. The more electronegative element has more electron density around it, and it'll give it a slightly negative charge and a slightly positive charge on the other side. We'll talk about that more in a minute. So this octet rule, this getting to the closed shell configuration on all the atoms in the molecules, that's the driving force for Lewis dot structures. And you can do it by single, double, or triple bonds. You can share one pair of electrons, 2 pairs of electrons, or 3 pairs of electrons. And now I'm going to start writing the shared pairs as lines. So that is a shared pair of electrons. Here's a double bond. Both of those represent a pair of electrons. So I count up the electrons around oxygen, 2, 4, and you count all the shared electrons, 2, 4, 6, 8. That oxygen has a stable configuration, 2, 4, and since you're sharing, this oxygen gets to count them as well, 2, 4, 6, 8. And you can see we could do that with single, double, and triple bonds. The combination of lone pairs and bonding pairs adds up to 8. When you get bigger molecules, we tend to stop putting the lone pair dots there. After a while, we know they're there. We have these halogens with their 3 lone pairs about them so often that we often don't draw them. We can draw them in when we need them to talk about the chemistry. We all say that they're there. Interestingly, though, these in the center, these are closely adhering to the octet rule. So they are making sure there's 8 or 2 electrons about the atoms. These on the sides, this is an electron deficient boron. So that didn't quite obey the octet rule. 2, 4, 6 electrons still actually forms a molecule. And you can expand octets to go beyond octets around central atoms. And this happens when you get to bigger atoms. And you probably you might be able to predict why. That would be a good chem quiz. Why do you think as you get to the bigger elements that's possible? And for the bigger elements, for these smaller ones with limited number of electrons, the closed shell is just the S's and the P's. But to close these shells and the bigger things, the d orbitals are coming into a play. So when the valence electrons are also the d, you have more valence electrons and more kind of pairing you can do. So you're not talking about an octet that's stable anymore, but uh, higher numbers of pairs of electrons. Okay, and here's one xenon tetrafluoride, 4 xenons and 2 lone pairs, and then there's sulfur hexafluoride, 6 fluorines, 6 bonding pairs about the sulfur. Okay, what's the correct Lewis dot structure of formaldehyde? So now we can start to do this, and this is one of the things, one of the goals of the class is go from the chemical formula to some kind of structural arrangement and start to talk about the bonds. So we can go from this, which is generic CH2O. All of these are CH2O. That means they're isomers, same number and kinds of atoms, but different configurations. They're isomers. Which isomer and which Lewis dot structure is the best, in your humble opinions, for that? So we'll try this again. I will start the poll. Ding, maybe. And yeah, I don't want to do this every time. Okay, we're gonna go into breakout room and see if you guys can see this. Okay, let's come back together. Push a button if you have not responded yet. There's around 75 of you responding. Low attendance might be a little low this morning after the midterm. You're all tired. Let's see what you're thinking. Oh, Lord. I have to push so many more buttons. Oh, and of course, sorry guys, I do not see. Maybe I stopped and restarted. I can't see your responses. I think we collected your responses that time, and I think it was operator error on my part that might have closed the quiz before we looked at the distribution. Learning curve, too high. Let's talk about it though. So you could have tried to draw the Lewis dot structure from scratch, and that's fine. You also could have just tried to evaluate the quality of the ones that are there. And I'll tell you in advance, on an exam, I can't just ask you to draw a Lewis dot structure. I mean, I can, but I know that none of you guys do this, but you can just Google the electron dot structure and it's going to come up. Okay. So it's crazy for me, even though I trust and love each of you individually. It's not a question that's going to come out in the exam. You're not going to have to draw one. You're going to have to do stuff more like this. You know, tell me something about it. I'll give you one and you can evaluate its quality. So this is more likely what you'll see. But how do you draw them? You do have to know how to do that. You count up all the valence electrons. We've done that already. You look at where they are in the periodic table. Carbon has 4, oxygen has 6. There's 2 hydrogens, each with 1. So a total of 12 valence electrons. So you have to use those 12 to glue the thing together. And you glue it together by using single and double bonds and put the rest as lone pairs. You want to get to octets. So this one we throw out right away because carbon has exceeded 2, 4, 6, 8, 10. It's exceeded the octet, and carbon is not one of those things that's going to do that. You have to get down to that n equal 4 kind of quantum level to do that. So you're not going to see that happening. N equal 3 will do it as well. So you have this one over here, which looks good. Everybody has their octet, but there's too many electrons, more than the valence 12 electrons. This one here, everyone has an octet and 12 total electrons in the bonding. And that gives me the correct or the best Lewis dot structure. This one is also 1, but it's not that good because the octet was expanded. This isn't really even a contender because the wrong number of electrons totally. This one would have some kind of charge on it, -2 charge, too many electrons. Okay, how many bonds are needed to complete the structure of the cyanide ion? We'll talk about this one together. So I have to complete cyanide, Cn, and it has a negative charge, the overall molecule. That means all the valence electrons are there plus an extra one. So I can count up the valence electrons. If I'm good, 4 for carbon, and nitrogen 5 plus 1 is 6, so 10 total electrons. How do I fill those up? Well, here's a good way to start your Lewis dot structures is right. And you may not know the central atom. Here, there's no central atom. Start your Lewis dot structure by bonding them together. Put one bonded to the other one with a single bond. And then start putting the electrons on. And if you start to run short, you're going to have to make multiple bonds. If you have extra electrons, you're going to have to use lone pairs. So we have to put 10 around there. So the way to do that is to add the electrons like that. I kind of run short. I have to share a lot. So I write that Lewis dot structure with a triple bond between carbon and nitrogen. And that is the cyanide ion. That's the poison that all the spies in the movies take. Extremely poisonous. Sodium cyanide. I don't know if they use sodium cyanide, but whatever. They use some salt of cyanide, I think, in the old days. Today, maybe there's a fancier, I have to die. Kind of a bad job. Poison. Okay. Interestingly, molecules can be isoelectronic as well as atoms. So a 10 electron system could have been C and N with a minus charge, or 2 nitrogens, each with 5 valence electrons. So isoelectronic. And if they're isoelectronic, that's likely going to have the same Lewis dot structure. So that kind of helps you as you get more experienced. Oh, poop. Oh, poopy. Okay, so here I have a bunch of all the editing that I was doing last night is just stacked up here. Stand by. Do we have our standby music? Get that queued up, and we put something on the screen. Technical difficulties. I just finished completely. So that means I have to go to the next. Can't find the mouse. There it is. So we are up. We just did resonance Lewis structure, so we have to go to this one. It looks like that is the one I should try to run. Yep, we'll start here. And we're back. Cut to me. Camera on me. So we've talked about Lewis structures. We're just going to continue talking about them, and we're going to take more tools to evaluate their quality. So the idea that we can put those octets in is one of the things that helps us. There's a couple other things. Let's go back and review the kinds of bonds. So in the ionic bond, the more electron element captures the electron, and I can't say it enough, if you take nothing else home from Chem 1, take home the fact that ionic bond, it's the plus minus attraction of the ions that's holding it together, and that's the strongest interaction you can get in bonding. So super strong because of that perfect full plus attracting a full minus, and they also have a lattice energy that we saw that helps them. Perfectly covalent, our rare perfect covalent is you share those absolutely equally, and you would only do that if the electronegativities of the two elements are the same. And obviously the way to do that is they're homonuclear. So homonuclear are the only perfect covalent bonds. Some are quite close because electronegativities can be close. And then the most common is polar covalent. And this is what I was saying we would get back to with the HCl molecule. Cl very much more electronegative than hydrogen. So in this bond, the electron density is concentrated around the chlorine nucleus. And what we write are these little delta. This is the Greek letter delta, plus and delta minus. And for some reason, this gives freshman chemist fits. All we mean, delta is just partial. If you know your math, you know the script delta is the partial differential. Here it's a partial charge. So not full one is all we mean. Some charge a little less than +1 here and less than -1 charge there. So not a full charge, a partial charge, partial plus there, partial minus there. Nowhere near full plus and full minus, because if that would be ionic. So this is no deltas here. This is full plus and full minus. Here, just a little negative character on that side of the bond and a little positive character on that side of the bond. That makes the bond polar. Polar bonds have something we call a dipole moment due to that unequal sharing, due to the fact that this end of the molecule is slightly positive and that end of the molecule is slightly negative. We've seen already that if you have those dipoles, a plus and a minus, those things are affected by electromagnetic radiation because they start moving if you have that oscillating electric field come through. So these guys are sensitive to much electromagnetic radiation. The entire molecule starts moving. So rather than electronic transitions, these guys are going to start rotating and tumbling. That's how a microwave oven works. Maybe we'll talk about that. We should talk about that. It's interesting. Oh, well, let's just talk about it. Water's one of these. Water's famously polar, has positive and negative ends. The oscillating electric field comes through of a microwave radiation, and that literally grabs onto that positive and negative charge separation in the molecule and starts it rotating. And that energy is transferred to the other molecules, and you get more motion in the system, and that's hotter. And it happens very fast, and that's why microwave ovens can heat so fast without a flame. Go explain that to your friends and relatives when they can't leave the room. So you can have this dipole moment for a single bond. In fact, every bond is really going to have some charge separation. So every individual bond has a little dipole, but the overall molecule might not, because they're little vectors and they can add to zero. A dipole moment has a magnitude and a direction. And I'm going to write the direction from the positive to the negative. So the little vector is pointing in that direction. That's important because when I start adding them up, I have to know which direction they're pointing to know if they cancel each other out. And I think you could see if I have some symmetry. So here's a 3 atom molecule or more, but the dipoles of that bond and that bond perfectly cancel each other out, same size and magnitude. So symmetry can eliminate your dipole because all the little individual dipoles add to zero. Asymmetry, this is the water situation, that gives you the dipole, the dipole back. Okay, so different magnitude, same arrangement of the atoms, same arrangement of dipoles, but different magnitude. So a bigger electronegativity difference there, causing a total dipole there. Here, simply the symmetry says you'll have a full dipole. And you can write you would add these as vectors and you'd have a sum vector that's the dipole of the molecule by adding the two individual ones. We're not going to do that extensively. We'll do it with pictures, of course, just like that with the arrows. Oh, well, here we go. Which one of these molecules is transparent to microwaves? Okay, so I have carbon monoxide, carbon dioxide, and there's that formaldehyde that we talked about just a minute ago. Let's talk through this together. Having such a hard time with our Chem Quizzes, running the software. So what do you have to look for? You have to look for that permanent dipole moment, the dipole moment that says I have a difference in electronegativity along some bond somewhere, and all bonds have some. Carbon and hydrogen are quite similar in electronegativity, so the carbon-hydrogen bond is not particularly polar. Carbon-oxygen bond is polar, and you have those everywhere. So here comes our microwave energy. Oh, there's even a little animation. So here comes our microwave, and I've emphasized the oscillating electric field, and the oscillating electric field starts moving that positive and attracting that negative, and it starts that guy rotating. There's no animation. I thought it was animated. Oh, let's see if it animates here. Here comes the electric field. It can repel that positive and attract that negative. And as it goes through, start that guy rotating. So that's how your microwave oven is heating up your food. The more moisture in your food, the more effective it is, because water is the primary molecule with a permanent dipole moment in your food. So there's the three of them. I'm going to draw the dipole moments of the bonds. I'm going to be annoyed at myself because I drew that one backwards. So we're going to draw the little dipole arrows from the more positive to the more negative. Here I did it backwards. Oxygen's the more electronegative element. So the negative is here. I'll just fix it. Carbon is the more positive and oxygen is the more negative. So there's that little delta negative there and the little delta positive there that has that. Have to go back and fix that. Here you're going to have the bonds in the molecule and the sum of all the dipoles. Here they perfectly cancel. So no dipole moment there. Here, a little dipole going up. The hydrogens are not, that's not a very polar bond. So a little bitty dipoles, and it wouldn't matter anyway, because this one is bigger, asymmetric, and you have a permanent dipole there. So these two would absorb microwave energy, and the carbon dioxide would not. Transparent. Microwaves go right on through. Transparent to microwaves, just like visible. These absorb it. And we don't get to it in this class, but the rotations are quantized. It's really freaky. This molecule cannot rotate at any frequency, at a range of frequencies. There are certain rotational frequencies that are favored by the system. And so you have rotational quantization. And if you take a little more chemistry, you'll go through and see that. And vibrational quantization as well, of vibrational modes and rotational modes. So let's talk about something we call resonance and bond order. So as we're looking at Lewis structures, we'll see this very quickly, that there's often several ways to write the same thing. In this case, this ozone molecule, O3, the double bond could be there or there. The actual molecule is, the bonds are the same. They're indistinguishable because there's quantum mechanics, there's wave functions overlapping here. This is not what's happening in reality. There are not pairs of electrons stuck between these atoms. But the Lewis dot structures still give us some predictive power because this you can see is something like the average of those two. So if you spend half your time in this configuration and half your time in that configuration, and you can easily flip between them, on average, you would have the same bond length and the same bond energy, the same bond strength. So we give that a bond order. So the relative strength or magnitude of the bond is the bond order. And rather than being bond order 1, a single bond, or bond order 2, a double bond, this oxygen is bond order 1.5 because I have those 3 bonds to share between 2 positions. So 3 pairs of electrons shared between 2 positions, 3 halves. That's bond order of 1.5. Here's the carbonate. Now I have 3 possible resonance structures. These are all equivalent, and the double bond could be on any one of the oxygens. And now carbonate is an ion with 2 negative charges. The negative charges bounce around, but the whole molecule does not do that. The whole molecule has a negative charge, a -2 charge on it. It cannot be localized anywhere on this molecule. This bond order 1 1/3, because I have 1, 2, 3 bonds to form and 1, 2, 3, 4 bond pairs. So 4 bond pairs over bonds that I want to form 3 gives me 1 1/3, 4/3 bond order. Benzene, C6H6. You'll see this a lot. We won't do it too much, but when we start to draw these Lewis dot structures, we get lazy very fast. And carbon-containing molecules, hydrocarbons, we just draw a vertex. And wherever there's a vertex without, where 2 lines come together, we say there's a carbon there. And then the organic chemists, so they're electron pushers, they're cooks, and they're lazy. They don't even draw the hydrogen. So it's C6H6. They're not lazy. Some of the finest chemists in the world, organic chemists. And the organic chemists, there's something called a physical organic chemist who I relate to better, because they are interested in the quantum mechanics and the physical interaction of the molecules. They still cook them, but they do all the work, and they tell you something about them as well. So become a physical organic chemist. So this, the double bond being in this position or those positions, same thing. So the bond order is 1 1/2 again. I have 1, 2, 3, 4, 5, 6 bonding sites, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs over 6 spots gives me 1 1/2. Is that what it gives me? Why does that not seem right? I have 1, 2, 3, 4, 5, 6 bonds to form, and I have, so there's a 6 on the bottom, and there's a 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds around there. That's 1 1/3. Wait, what am I doing wrong there? 1 1/2. Yeah, it should be 1 1/2, because there's, it looks 1 1/2. 1, 2, 3, 4, 5, 6. Half of them are double bonds, half of them are single bonds. Yeah, that's what I did. 9, 6, 1. Oh, that is 1 1/2. Okay. Sorry. Somehow unable to do arithmetic. So let's talk about where the you saw me start to draw negative charges on specific atoms there, even though they were covalent bonds. Those are partial. I need to know where they are and how to find them. For the most case, we just use the difference in electronegativity and say the more negative, the more electronegative is, the more negative character you have on the bond. That's where the electrons spend more time. So, but we can formally draw it out, and we can say, what's the formal full charge, a full formal charge on each atom? So we define this in by just doing a little formulaic work. We write the Lewis dot structure. This one, I count up all the valence electrons and add 1 because it has a negative charge. I get this Lewis dot structure with the 1 1/2 bond order. And then I say, I'm going to kind of pull it apart and equally share all the electrons, or share them, you take half and I take half kind of situation. So here the nitrogen, I've pulled it off, and I say, I can take half and you can take half. And I'm going to share equally the electrons there. So nitrogen, you can have 2 and I'll take 2. And over here, I'm going to say this bond here, nitrogen, you take 1 and I'll take 1. So I've pulled it apart, shared those equally. I've pulled that apart and shared those equally. So it's kind of, it's just a formalism. You share the electrons, pull it back apart, share all the bonding electrons equally, and then you compare that arrangement to what it would be on the atom. So oxygen has 6 valence electrons, nitrogen has 5, oxygen has 6. But in this molecule, if we do this distribution where we pull them apart and share that one of them, both of them can count it, essentially. Say, you can count it and I can count it. And what we have is oxygen in the molecule has more electrons that it can share than it does as an atom. So that's where the negative charge ends up. So these two formally charge 0. In this structure, when I do that sharing, there's 5 and there's 5 in the atom. There's an extra one in the molecule than the atom, so that's where the negative charge resides. The reason we do it is that helps us evaluate the quality of our formal charges. Actually, the quality of our Lewis structures. So I look at the formal charge and say, are the formal charges on the more electronegative elements? So how does the formal charge change in this experiment? So let's just go through and talk through another one. I'm going to go from NO2 minus to NO3 minus. That's an oxidation, adding oxygen, oxidation, but it's a formal oxidation. And that the oxidation number of these is going to change. We'll talk about that in a minute. Formal charges, do they change? So I go from a negative charge on NO2 to a negative charge on NO3. We can just do the same counting again. In the molecule here, 5 electrons, gonna of those 4, I'm gonna share 2. That's a lone pair, so I get to keep that. And of these 2, I'm gonna share equally and take 1. So that's in the molecule. Same thing over here. You say, well, there's 4 there. We're gonna share. I'm gonna take 2. You take 2. This now there's an oxygen there. So if I share that, you take 1. I take 1. I have 1. Oxygen, I'm going to share. You take 1, I take 1, leaves that 1. Okay? So nitrogen has a different number of electrons in each one. Nitrogen is an atom. That's always the same, has 5 valence electrons. So the formal charge changed from 0 to +1 on the nitrogen. So 4, when I did that sharing thing, 5 when it's an atom, so it looks different between an atom and the molecule, and it has 1 fewer electron, so a positive formal charge there. So it increases. Okay, we're kind of out of time, so we'll go and we'll talk about the bond order in sulfate next time. And we'll again do the bond order, we'll do the formal charges, and evaluate structures of the sulfate ion SO4 - 2 tomorrow. And we'll also do our midterm bonus question. It seems like we've got the quiz software working. So we'll take the most missed question on the midterm. We'll present it to you. You'll get to talk about it amongst yourselves and vote on it again and get that point back. That's it. Are there any questions that we should address in the chat or anything? Okay, so we'll see you tomorrow.